Through previous learning, we know that a circuit is composed of a power supply, a load and an intermediate link. When the circuit is working, we not only need to analyze physical quantities, its structure, but also analyze the working condition of the circuit, also called the basic variables of the circuit, including current, voltage, electromotive force, etc. Next, we will learn them one by one. First, the basic concept of current. Only moving charges can drive electrical appliances. In physics, the directed movement of charged quantity of particles is called current. The magnitude of current is the charge passing through a cross-section of a conductor per unit time, which is represented by I. Q represents the quantity of charge. T represents time. The formula for calculating current is I equals Q divided by T. In the formula, P represents the quantity of charge passing through the cross-section of conductor. The unit of current is ampere. Second, the direction of current, the actual direction. The directional movement of charged particles forms current. Current is a vector which has a direction. It is usually stipulated that the direction of positive charge movement is the actual direction of current. So in components, there are only two actual directions of current. It can be from A to B or from B to A. However, for complex circuits, or the current in the circuit changes with time, the actual direction of the current is often difficult to predict. We introduce the reference direction of current. We arbitrarily assume a direction of positive charge movement as the reference direction of current. We regard current as an algebraic quantity. If the actual direction of the current is the same as the assumed reference direction, the result is positive. The actual direction of the current is opposite to the assumed reference direction. The result is negative as shown in the figure below. Third, types of current. Current is a physical quantity with both magnitude and direction, whose magnitude and direction do not change with time, are called direct current. Is represented by the letter DC. To represent in the circuit diagram, a horizontal line is used to represent direct current. A current whose magnitude and direction change with time is called alternating current. It is represented by the letter AC. In the circuit diagram, is represented by a waveform curve. As shown in the figure below, it shows the waveform diagrams of the two currents. First, voltage. Voltage is a physical quantity that measures the ability of electric field in the international system of units. The unit of voltage is volt. If a positive charge moves from point A to point B, the work done by the electric field force is W. The work done by electric field force to move unit positive charge from point A to point B, which is equal to the voltage between point A and point B. Then the voltage between A and B is UAB, is equal to W divided by Q. In the formula, UAB is the voltage between points A and B. W is the work done by the electric field force. Q is the electric quantity. Second, potential. Potential is a physical quantity that measures electric potential. Energy is equal to the work done by the electric field force, moving a unit positive charge from this point to the reference point. Numerically, that is V equals W divided by Q. In the formula, V is the potential. W is the work done by the electric field force. Q is the electric quantity. Voltage is the potential difference between 2 points. The relationship between voltage and potential is expressed by the formula U. UAB equals 1 minus VB, where VA is the potential at point A, and VB is the potential at point B. Third, the direction of voltage. If the direction of potential decreases, However, in complex or alternating circuits, the actual direction of voltage between 2 points is often difficult to determine. It brings difficulties to the analysis and calculation of actual circuits. Therefore, the reference direction of voltage is used. It is assumed that the direction from high potential to low potential is the reference direction. Similarly, when analyzing circuits, when the reference direction is consistent with the actual direction, then U is greater than ln. Otherwise, U is less than ln. The reference direction can be represented by an arrow or positive and negative signs. Electromotive force is an important physical quantity. To describe the nature of a power source in the power supply, under the action of electric field force, positive charge flows from the positive pole to the negative pole. Similarly, inside the power supply there is also a force, push positive charges from the negative pole to the positive pole. This force is called non-electrostatic force. The non-electrostatic force constantly moves positive charges from the negative pole to the positive pole. It converts other forms of energy into electrical energy to keep the voltage across the power supply constant. The ratio of work done by the non-electrostatic force to the amount of electricity of the moved charge is called the electromotive force of the power supply. As shown in the figure, the level of 3.7 volts on the lithium battery is the electromotive force level of the battery. When current flows through a load, it's called electrical work, represented by W. An electrician is denoted by W. The work done W is equal to U current multiplied by the time T. The international unit of work is joule, but in practice, is often expressed in kilowatt hours or degrees. Second, electrical power. The power P represents the speed of current doing work. Its magnitude represents the work done by the current. Per unit time, P equals the work done by the electrician, divided by time, E equals voltage multiplied by current. The international unit of power is the watt, abbreviated as W, and also kilowatts and milliwatts are often used. Through the above learning, we know that current is a vector with magnitude and direction. Before analyzing the circuit, we must select the reference directions of current and voltage. The reference direction can be changed, but the actual direction of voltage and current remains unchanged. When calculating electrical work and power, we must pay attention to the unit conversion.